Okay. Uh, Let me now go to one important system in a binary system, which we call as Eutectic system. Don't read right now what is written here. Only want to read. I only want you to read this. That Eutectic means low melting point. That is what is required for the time being. Eutectic means low melting point, or specifically lowest melting point. So rest of it I will explain. So don't spend time on reading it. So we have eutectic, which we say means lowest melting point, or what we call as easy melted. Okay, what is the meaning of this? Let's come to this. The meaning of this happens to be that if I have, let us say, two component phase diagram, A and B, any component can be there. So let us say A happens to be a melting point. This is the melting point of A, TMA, and this is the melting point of component B. So normally we have seen in the case of isomorphous system that okay, this is the A, this is B. Uh, any in between you may have that, okay, we said that, okay, it may happen something like this, that I may have a range in which the melting point of the resulting alloy will be lying. But that's not always the case, specifically in the case of non-isomorphous systems. So what happens in the such cases, one of the simple examples happens to be a tin lead solder that you use in the case of your soldering iron, the soldering compound that you see here. So what is observed is that when you start mixing A and B, which may be tin and lead only or something else also, there may be one specific composition which gives you a melting point here, which gives you a very low melting point, even lower than the constituents A and B melting points. So that composition, which we say is easy melting, is then referred to as the eutectic composition. That is, it will have a very low melting point. We will explain it briefly right now. Okay, so eutectic point, if I define, is the point where the liquid phase borders directly on the solid alpha and beta phase. Okay, so before coming to this, let me now see that it is not a isomorphous diagram. Why it is not an isomorphous diagram? Because you have two solid phases, alpha and beta. In our earlier case, it was only a single phase solid, alpha. Right now, it is a two phase solid. That means you have alpha also, you have beta also. Let us explain it further. What is the meaning of that? We explained one, we have just given a definition that a eutectic point is a point where the liquid phase border directly is to the solid alpha and beta phase. Means normally you have seen that in our last diagram that you have the liquid phase, then you had liquid plus solid phase, and then you had the solid phase here in the previous diagrams. But there may be one point where you find that liquid phase is directly going into two solid phases. So this liquid L, at this point, when it is of particular composition only, it transforms into two solid phases. So that is the point which we refer to as the eutectic point. So this is a very important point in the iron carbon diagram also, and that is why the definition of it is required. That what is the definition of the eutectic point? Okay, let's come to one more phase diagram, and then we move on to the FEC or the iron carbon diagram here. This one is called the copper silver diagram. It is not a copper nickel diagram, it is a copper silver diagram. Copper silver diagram. So what we see here, same temperature, composition. We are plotting as percentage of silver. Percentage of silver. So it is pure silver. This is pure copper. This is pure copper. And this is pure silver. Okay. So when you start, let's look at the other points. the melting point of copper, the melting point of silver, the melting point of copper and the melting point of silver. What will happen? Here I have pure copper, 0% silver. When I start adding silver into that, you will start forming what we call as a solid solution. What are these solid solutions? When I start adding silver into copper here, you start forming a solid solution. You add certain amount of it, and what you observe is that there is this region which we say is the alpha region, so here the blue one. Again, a single phase region, a single phase solid region, which is alpha, which is what it contains some amount of silver. But that silver that you have added into it, it is actually giving only a single phase. It is not precipitating out into a second phase. Means it is within the solubility limit of that you are putting silver into it, but it is soluble in copper. And that is why what you observe is that you don't observe two phases, you only observe a single phase alpha here. And that means now this region is also having a different shape now. Why it is so? Because we find that the solubility limit is temperature dependent. We already saw that. So as you increase the temperature, you find more and more solubility is increasing here, and then we find that you again go to this region. Okay. Then similarly, when you look at the right hand side, you have the beta phase. So I am defining here what is alpha and beta. So alpha is a solid phase, the solid solution rich in copper, and it has silver as a solute component. And beta is opposite. Beta is having copper as a solute component. Both of them have FCC structure. And now there are other lines here. So I say that this is the liquid region. This is the liquid region. And that means now I have this line which we say is the liquidus line. Means above the liquidus line there will be only liquid. I have one point here which I see is happening at a composition of 71.9% of silver, which seems like a low melting point alloy. Means it seems like an eutectic, where we find that a single liquid phase is transforming directly into two solid phases, alpha and beta. It is not happening at any other composition and any other temperature. This happens at a temperature which is we call it as T eutectic, and at a particular which is 779 degrees for this particular reaction, and at a composition of 71.9% of silver. So that is why we have a eutectic reaction. Means it's a low melting alloy. If I create a alloy of copper and silver which has 71.9% silver in it, it will melt at 779 degrees. It will be having very low melting point, and it may be desirable for us certain times for having low melting points. Okay, so what are the other lines which are visible to us, because it is not a isomorphous diagram, so it has other lines also. So let us see what are the other lines here. I will come to the next slide and where we will explain that. We will explain. So we are saying here BC, this BC is the solvus boundary, means it is the boundary of solubility limit, solvus boundary. Similarly, this GH is also the solvus boundary. Solidus line is now not a straight line, because if you remember our previous one, it was a straight, it was something like this here, and here this was the liquidus line and this was the solidus line here in the isomorphous system. Here we find that the solidus line is something like this, moving like this, and then it moves along this isotherm. This isotherm, which we say is eutectic isotherm. Isotherm means which happens at constant temperature. So this is happening at a constant temperature. So this is the solidus line. So when I say this is the solidus line, it means now that below this line there will only be solid. Below this line there will only be solid. So we are defining it again here. Let's say come to this slide here. So you have the solvus line given as BC and GH, BC, and this was GH, which is the solid solubility line. The solidus line now happens to be A, B, then this is F, G, and then it's B, E, G. This is G, and this is F. This is F. So A, B, this one, A, B, B, E, G, this is G, and G, F. So this is the solidus line now. So above the solidus line, you have two phases, liquid plus solid. Above the liquidus line, you have only a single phase liquid. Below the solidus line, you have only two solid phases, not a single solid phase, because single solid phase is available in this region up to limited solubility. Within BC, it is only alpha. But if you put more silver into it, a second phase beta will precipitate. Simply just like water sugar, that if you put more sugar into it, you will have syrup plus sugar available separately. So same thing happens here, that when you put more silver into it, more than the solubility limit, you have the second phase evolving, which is the beta phase. So the invariant point, or what we call as the, I've already said that this is the liquidus line, that is A, E, F. So this happens to be your liquidus line. The liquidus line. The maximum solubility, maximum solid solubility, keep it in mind that you have solid only below this line. That is, we are saying that it is below this. Up to this line is the maximum solid solubility. The maximum solid solubility of alpha phase is 8%. It is nearly, let us say, 8% here. And beta is around 8.8%. It is, let's say, 8.8% here. 8% of copper. And I have an invariant point at E, which we say invariant means it won't happen at any other composition. It will not happen at any other temperature. So this invariant reaction, which we say is the eutectic reaction, a low melting reaction, happens at only this particular composition, where and this particular temperature only at point E, where we find that alloy having 1.9% of silver will melt at 779 degrees centigrade, and then you will have this liquid transforming directly into alpha and two solid phases. Whereas at any other point, what you observe, you have liquid, then you have two phases, liquid plus solid, then you have solid. But here at this point, it is observed that you have liquid, and then I have directly coming the two solid phases. Keep it in mind, eutectic reaction, a reaction where a single liquid phase transforms into two solid phases. That is very, very important. And we have an invariant reaction in the case of iron carbon diagram also. And that is why I'm explaining that what is the meaning of the what we call as the this eutectic reaction here. So we say this is the eutectic reaction here. So eutectic reaction, I already again defined that an isothermal reversible reaction between two solid phases during heating of a system where a single liquid phase is produced, or opposite of it, because it is written here reversible. So when you start heating two or more solid phases, here there are two, alpha plus beta, they actually during heating go into a single liquid phase without going into your liquid plus alpha plus beta. That is not happening here. It is happening from liquid, it is directly going into alpha plus beta. A single solid liquid phase is transforming into two solid phases, or vice versa, because it is a reversible reaction. So the eutectic reaction here means that a liquid of a composition CE, a eutectic composition, transforms into alpha plus beta. Alpha plus beta. Keep it in mind here that I'm not writing alpha composition as E. It is C alpha E. Means the composition is different. C beta E. But we need to understand what is the eutectic reaction. I hope it is clear that for this particular phase diagram, which is a copper silver system, this happens at 71.9% of silver. Okay. The similar reaction happens in the case of your, as I said, your your soldering compound, which is a alloy of tin and lead. We find that a soldering compound, when you see the diagram here, you can very easily see that this is the point which is the low melting point, the lowest melting point, where your liquid is converting directly into alpha plus beta, and it happens it happens that it's around 60-40% of your tin. If you have 40% lead and 60% tin, we actually it is 61.9% tin. You observe that it has a melting point of 150 degrees, which is lower than the melting point of tin separately and lead separately. So we find that this is how it is observed as a eutectic point in the case of your lead tin system also. Okay, let us try to answer something which we already know. And please pay attention for a moment. What we find that the first thing, when you are at this point, eutectic point, the phases present just below the eutectic point are alpha and beta. We already know that. Okay, is done? If you want to find out at any point within the solid region, that is alpha plus beta region, what is the relative, what is the phase composition? What is the phase composition? I can simply find out with the help of the tie line here. So let us say if this is the point here, or the point can be here on the eutectic point also. If this is the point, the where C naught happens to be 40%, means the alloy composition happens to be 40% of tin, 40% tin. And at this point, if you want to find out the composition of alpha, because it has got two phases, alpha and beta. So I draw a tie line, which is shown here. This is the tie line which is shown here. It intersects the one boundary with the alpha phase. It intersects the second boundary with the beta phase, or it is intersecting the solvus line here. So we already said, if you remember, when you use the tie line approach, we said you draw a tie line from the constitution point, and wherever the tie line is intersecting the boundary between the two phase region and the other one phase regions there, it was liquid there. But right now I am seeing here that there are two solid phases, alpha and beta. This one is a single solid phase, alpha, and this one is a single solid phase, beta. So I can apply the tie line here also, means the intersection point is given here for alpha, and I will read that what is alpha. The composition of alpha comes to 11%. Means this point, at this point, the constitution point which you're referring, you have the alloy which is having existing in two phases, alpha and beta. The composition of two phases is given by the tie line rule, and it tells me that composition of the alpha phase is 11% of tin. And similarly, composition of the beta phase, you see the intersection line here, it is around 99% tin. So the intersection, the tie line gives me, so this is answer we are getting from your simple tie line. The relative amount of phases we will get from the lever rule. So if you want to find out the amount of alpha, so alpha is on this side, so this is alpha side. So alpha side will be the length of the opposite arm. The opposite arm happens to be this one, which is written here as S. The length of the opposite arm S upon the total length, that is R plus S. R plus S. Similarly, composition of the beta phase. So beta is on this side, and about this point, the length of the opposite arm is R. So it is R upon the total length of the lever is R plus S. R plus S. And this gives me that what is the what you call as the relative amount of each phases. How much of it is alpha and how much of it is beta. So at this point, your constitution point, we are able to find here that you have 67% of alpha phase and 33% of the beta phase visible to you. If you look at it in a microscope, you will find that if you had only a single phase region, you had only, let us say, a single color ones, only the grain boundaries, and then the same colored grains were there. But if it is a two-phase region, we observe that now there will be multiple phases, maybe two phases here, in which what we observe is that you have a dark phase which may be there at the grain boundaries, and you have the light phase which may be the alpha phase. So it may be written as alpha phase, and then I may write that this is the beta phase here, because there are they are not physically and chemically distinct. They are different. They are not chemically distinct because we have seen that the amount of tin in them is different. This contains 11% tin, this contains 99% tin. So chemically they are not same. Physically they are not same. I hope it is clear. Yes. Yes.
सर अगर पॉइंट इसके यूटेक्टिक लाइन है उसके अबव दिया हुआ हो तो वहां कैसे फाइंड करेंगे?
अबव वाले में तो बेटा सिंपल ही है ना. इफ इट इज अबव द यूटेक्टिक लाइन, it is here in the liquid region, it means it's single phase liquid.
नो सर, यहाँ पे जहाँ पे लिक्विड एंड अल्फा दिया हुआ है.
Liquid plus alpha, say this one.
यस सर.
So if the constitution point is here, let us say I am at this point. Can you see this point?
यस सर.
Okay. So if I point this, किसको कुछ लिख लेते हैं, मान लीजिए A लिख देते हैं. Let us write it as A. Let me first erase this. कुछ थोड़ा सा erase कर देते हैं. Just a minute. Let me first erase a bit so that it is clear. Okay. Okay. So point आपका मान लीजिए यहाँ पे आ गया अब, ठीक है? Is it clear?
Yes, sir.
Constitution point is here. Now you draw the tie line. You draw the tie line as you draw normally. So this tie line, which is drawn from a region which is a two-phase region. ये दो-phase region है, liquid plus alpha.
Yes, sir.
अब ये टाई लाइन हमने ड्रॉ कर दी. एक तरफ इंटरसेक्ट करा अल्फा को, दूसरी तरफ इंटरसेक्ट करा लिक्विड लाइन को. तो आपका जो अलॉय कंपोजिशन था, मान लीजिए वो ये था. इट वाज हैविंग, जो आपने स्टार्ट किया था, मान लो आप हीट करना स्टार्ट कर रहे थे, यू स्टार्टेड विद लेट अस से इट इज 38% ऑफ 10, कुछ ऐसे है, 38% है. तो ये अलॉय आपने 38% से स्टार्ट करा था. अब आप ए पॉइंट के ऊपर आ गए जहाँ पे ये सॉलिड अल्फा प्लस बीटा नहीं है, अब ये लिक्विड प्लस अल्फा आ गया. Now, I know that it is liquid plus alpha, so it is intersecting the alpha line here, alpha boundary here, and the liquid boundary here. इनको read कर लो यहाँ से बस. So you read this and you read this. So tie line बनाई आपने, तो tie line से क्या मिलेगा? Composition और what? Relative amount.
Relative amount.
Tie line. Tie line से composition मिलती है. ये बताया हमने इधर. देखो टाई लाइन से कंपोजिशन मिलेगी कि यहाँ पे दो फेज तो है. ये ए पॉइंट के ऊपर लिक्विड भी है और अल्फा भी है, दोनों फेज हैं. अब हमें ये नहीं पता कि लिक्विड के अंदर जो आपका ये लिक्विड फेज है, इसके अंदर कितना टिन है और अल्फा फेज जो है उसके अंदर कितना टिन है, ये नहीं हमें पता. ये हम जानना चाह रहे हैं. तो उसके लिए टाई लाइन ड्रॉ करेंगे. तो जहाँ पे जिन्हें अल्फा को इंटरसेक्ट करा, तो ये हमने रीड करा कि ये it will come to let us say 18%, means alpha has 18% tin. अब ये लिक्विड था, इधर लिक्विड को इंटरसेक्ट करा, यहाँ से आप रीड करें इट में बी अराउंड 50%. सो इट हैज, लिक्विड हैज अराउंड 50% tin. अब इसको ऊपर चले जाओगे तो फिर चेंज हो जाएगा. ये टाई लाइन यहाँ पे ये बन गई, नीचे आओगे तो और चेंज हो जाएगा. ये तो सेम चीज होगी ना जो मैंने लास्ट स्लाइड में एक्सप्लेन किया है, दैट ड्यूरिंग दिस जो ट्रांसफॉर्मेशन हो रही है उसमें कंपोजिशन जो है वो वेरी हो रही है कंटिन्यूसली. लिक्विड और अल्फा फेजेस, लिक्विड और सॉलिड फेज दोनों में से कंपोजिशन चेंज होती जा रही है, ऊपर से नीचे आते हुए और नीचे से ऊपर जाते हुए भी. इज इट क्लियर? सिमिलरली रिलेटिव अमाउंट फाइंड करेंगे विद द हेल्प ऑफ योर लीवर रूल.
यस.
टाई लाइन से बनेगी कंपोजिशन, लीवर रूल से मिलेगी रिलेटिव अमाउंट की जो लिक्विड कितने परसेंट है और अल्फा कितने परसेंट है, दैट इज योर रिलेटिव अमाउंट. वो भी यहीं से मिल जाएगी, इसी पॉइंट पे निकालनी है. तो इस अपोजिट से आप जिस साइड का लेना चाह रहे हो उसके अपोजिट कर दो. इधर लिक्विड वाले का अपोजिट है, आर्म हो गई आपकी ये वाली, दिस डिवाइडेड बाय द टोटल लीवर लेंथ, दैट इज गिविंग यू द वैल्यू ऑफ द the relative amount. I will tell you one more rule which is there. It's a very simple
सर
rule but very important rule.
सर अगर हमें टोटल अमाउंट निकालना है कि ए पॉइंट के ऊपर कितना टिन है और कितना लेड है, तो उसके लिए हमें क्या करना
टोटल
होगा
तो
कि
पता ही है
जैसे
बेटा। टोटल तो आपने कोई नेट देखो, तुमने एक अलॉय लिया, मान लो कि जिसमें 38% टिन था, ठीक है। आपके पास कोई बाजार से पीस मिला, उसमें 38% टिन है, ले आए तुम घर पे, ले आए इसको। अब इसको हमने टोटल तो पता ही है मेरे को, इसमें क्या पता करना, मैं आपको पता लगा कि ये टोटल इतना है। अब ये कैसे निकाला है उसकी बात नहीं अभी कर रहे हैं, अभी हम फेज डायग्राम में फेज चेंजेस की बात कर रहे हैं। तो व्हेन आई नो कि 38% टिन था, जब मैंने उसको हीट करना शुरू किया, तो व्हेन यू कम टू दिस ए पॉइंट हेयर, यहाँ पे मैं जानना चाह रहा हूँ इससे नीचे नीचे अगर सॉलिड ही है तो वो कोई प्रॉब्लम नहीं है। द प्रॉब्लम इज व्हेन इट कम्स टू दिस द एट दिस पॉइंट ऑल्सो। अब जो अलॉय कंपोजिशन 38% है, दैट इज क्लियर, बट अल्फा बीटा में कितना कितना है वो निकालने के लिए हमने फिर से टाई लाइन लगाई यहाँ पे, जो अभी मैंने एक्सप्लेन किया कि अल्फा बीटा के अंदर कितना टिन है। मींस से आपको समझ आ रहा है कि जो टू फेज रीजन्स के अंदर आपका जो टिन है वो ऐसे नहीं है कि 38% सारा डिस्ट्रीब्यूटेड है, अल्फा फेज में कहीं ज़्यादा है, बीटा फेज अल्फा फेज में कम है, बीटा फेज में ज़्यादा है। वो मूव करोगे तो वो चेंज होता रहेगा, एंड दैट इज व्हाट इज टोल्ड विद द हेल्प ऑफ द फेज डायग्राम। फेज डायग्राम बनाने का मतलब ही ये है कि सो दैट यू आर एबल टू फाइंड आउट द compositional changes which are happening when you change the equilibrium, because आप equilibrium change कर रहे हैं, आप heat कर रहे हैं या cool कर रहे हैं। pressure अभी हम कह रहे हैं कि constant है, it is why that is why pressure is not a variable here. Normally in our diagrams we are talking about temperature as a variable, कि उसको melt करेंगे या melt है वो है पहले से है उसको solidify करेंगे।
हाँ जी
Is that right?
यस सर।
Okay. We already have it's again a similar example which now this is what you were asking, is it? I had that, I forgot that I had it in the next slide. So जब आपका when your point is at the liquid plus alpha region, this is what you can read it. Then you can draw the tie line, C alpha Cl can be found, C alpha Cl. So tie line जो है वो एप्लीकेबल है इन एनी टू फेज रीजन। वो लिक्विड सॉलिड भी हो सकता है, दोनों सॉलिड भी हो सकते हैं। हमने दोनों सॉलिड में लगाई थी अभी यहाँ पे अल्फा एंड बीटा में। अभी आयरन कार्बन में हम सॉलिड में भी लगाएंगे इसको बार बार कि हाउ टू यूज टाई लाइन इन ए टू फेज सॉलिड रीजन। So the same example which I just answered is explained here in this